A Turing machine is a hypothetical device that manipulates symbols on a strip of tape according to a table of rules. Despite its simplicity, a Turing machine can be adapted to simulate the logic of any computer algorithm, and is particularly useful in explaining the functions of a CPU inside a computer. The Turing machine was invented in 1936 by Alan Turing, who called it an A machine. The Turing machine is not intended as practical computing technology, but rather as a hypothetical device representing a computing machine. Turing machines help computer scientists understand the limits of mechanical computation. Turing gave a succinct definition of the experiment in his 1948 essay, Intelligent Machinery. Referring to his 1936 publication, Turing wrote that the Turing machine, here called a logical computing machine, consisted of an unlimited memory capacity obtained in the form of an infinite tape marked out into squares, on each of which a symbol could be printed. At any moment there is one symbol in the machine. It is called the scanned symbol. The machine can alter the scanned symbol and its behavior is in part determined by that symbol, but the symbols on the tape elsewhere do not affect the behavior of the machine. However, the tape can be moved back and forth through the machine, this being one of the elementary operations of the machine. Any symbol on the tape may therefore eventually have an innings. A Turing machine that is able to simulate any other Turing machine is called a universal Turing machine. A more mathematically oriented definition with a similar universal nature was introduced by Alonzo Church, whose work on lambda calculus intertwined with Turing's informal theory of computation known as the Churchie-Turing thesis. The thesis states that Turing machines indeed capture the informal notion of effective methods in logic and mathematics, and provide a precise definition of an algorithm or mechanical procedure. Studying their abstract properties yields many insights into computer science and complexity theory. Informal description. The Turing machine mathematically models a machine that mechanically operates on a tape. On this tape are symbols, which the machine can read and write, one at a time, using a tape head. Operation is fully determined by a finite set of elementary instructions such as in state 42, if the symbol seen is 0, write a 1. If the symbol seen is 1, change into state 17. In state 17, if the symbol seen is 0, write a 1 and change to state 6, etc. In the original article, Turing imagines not a mechanism, but a person whom he calls the computer, who executes these deterministic mechanical rules slavishly. More precisely, a Turing machine consists of. Note that every part of the machine and its actions is finite, discrete and distinguishable. It is the unlimited amount of tape and runtime that gives it an unbounded amount of storage space. Formal definition. Hopcroft and Ullman formally defined a Turing machine as a 7-tuple where, is a finite, non-empty set of states, is a finite, non-empty set of the tape alphabet symbols, is the blank symbol, is the set of input symbols, is the initial state, is the set of final or accepting states. Is a partial function called the transition function, where L is left shift, R is right shift. Anything that operates according to these specifications is a Turing machine. The 7-tuple for the 3-state Busy Beaver looks like this. See state table below. Initially all tape cells are marked with 0. Additional details required to visualize or implement Turing machines. In the words of Van Emd Boas, PA6, the set theoretical object, his formal 7-tuple description similar to the above provides only partial information on how the machine will behave and what its computations will look like. For instance, there will need to be many decisions on what the symbols actually look like, and a fail-proof way of reading and writing symbols indefinitely. The shift-left and shift-right operations may shift the tape head across the tape, but when actually building a Turing machine it is more practical to make the tape slide back and forth under the head instead. The tape can be finite, and automatically extended with blanks as needed, but it is more common to think of it as stretching infinitely at both ends and being pre-filled with blanks except on the explicitly given finite fragment the tape head is on. The tape cannot be fixed in length, since that would not correspond to the given definition and would seriously limit the range of computations the machine can perform to those of a linear-bounded automaton. Alternative definitions. Definitions in literature sometimes differ slightly, to make arguments or proofs easier or clearer, but this is always done in such a way that the resulting machine has the same computational power. For example, changing the set to, where n would allow the machine to stay on the same tape cell instead of moving left or right, does not increase the machine's computational power. The most common convention represents each Turing instruction in a Turing table by one of 9 5-tuples, per the convention of Turing-Davis in undecidable, PA 126-127 and Davis PA 152, Definition 1, current state key, symbol scanned SJ, print symbol SK erase E none N, move tape 1 square left L right A none N, new state QM. Other authors PA 119, Hopcroft and Ullman PA 158, Stone PA 9, adopt a different convention, with new state QM listed immediately after the scanned symbol SJ. Definition 2, current state key, symbol scanned SJ, new state QM, print symbol SK erase E none N, move tape 1 square left L right A none N. For the remainder of this article definition 1 will be used. In the following table, Turing's original model allowed only the first 3 lines that he called N1, N2, N3. He allowed for erasure of the scanned square by naming a zeroth symbol SO equals erase, or blank, etc. However, he did not allow for non-printing, so every instruction line includes print symbol SK, or erase, undecidable PA 300. The abbreviations are Turing's. Subsequent to Turing's original paper in 1936 1937, machine models have allowed all 9 possible types of 5-tuples. Any Turing table can be constructed from the above 9 5-tuples. For technical reasons, the 3 non-printing or N instructions can usually be dispensed with. For example, see Turing machine examples. Less frequently the use of 4 tuples are encountered. These represent a further atomization of the Turing instructions. Boulos and Jeffrey, Davies Siegel Wiecker. Also see more at poster Turing machine. The state. The word state used in context of Turing machines can be a source of confusion, as it can mean 2 things. Most commentators after Turing have used state to mean the name designator of the current instruction to be performed, that is the contents of the state register. But Turing made a strong distinction between a record of what he called the machine's M configuration, and the machine's state of progress through the computation, the current state of the total system. What Turing called the state formula includes both the current instruction and all the symbols on the tape. Thus the state of progress of the computation at any stage is completely determined by the note of instructions and the symbols on the tape. That is, the state of the system may be described by a single expression consisting of the symbols on the tape followed by I, and then by the note of instructions. This expression is called the state formula. Earlier in his paper Turing carried this even further. He gives an example where he placed a symbol of the current M configuration the instructions label beneath the scanned square, together with all the symbols on the tape. This he calls the complete configuration. To print the complete configuration on one line, he places the state label M configuration to the left of the scanned symbol. A variant of this is seen in Clean, where Clean shows how to write the GAR paragraph del number of a machine's situation. He places the M configuration symbol Q4 over the scanned square in roughly the center of the 6 non-blank squares on the tape and puts it to the right of the scanned square. But Clean refers to Q4 itself as the machine state. Hopcroft and Ullman call this composite the instantaneous description, and follow the Turing convention of putting the current state to the left of the scanned symbol. Example, total state of 3 state 2 symbol busy beaver after 3 moves. 1A1. This means, after 3 moves the tape has 000110000. On it, the head is scanning the rightmost one, and the state as A blanks can be part of the total state as shown here, B01. The tape has a single 1 on it, but the head is scanning the 0 to its left and the state is B. State in the context of Turing machines should be clarified as to which is being described, the current instruction, or the list of symbols on the tape together with the current instruction, or the list of symbols on the tape together with the current instruction placed to the left of the scan symbol or to the right of the scan symbol. Turing's biographer Andrew Hodges has noted and discussed this confusion. Turing machine state diagrams. To the right, the above table is expressed as a state transition diagram. Usually large tables are better left as tables. They are more readily simulated by computer in tabular form. However, certain concepts for example machines with reset states and machines with repeating patterns can be more readily seen when viewed as a drawing. Whether a drawing represents an improvement on its table must be decided by the reader for the particular context. See finite state machine for more. The reader should again be cautioned that such diagrams represent a snapshot of their table frozen in time, not the course of a computation through time and/or space. While every time the Busy Beaver machine runs it will always follow the same state trajectory, this is not true for the copy machine that can be provided with variable input parameters. The diagram progress of the computation shows the three-state Busy Beaver's state progress through its computation from start to finish. On the far right is the Turing complete configuration at each step. If the machine were to be stopped and cleared to blank both the state register and entire tape, these configurations could be used to rekindle a computation anywhere in its progress. Undecidable PPA 139 140. Models equivalent to the Turing machine model. Many machines that might be thought to have more computational capability than a simple universal Turing machine can be shown to have no more power. They might compute faster, perhaps, or use less memory, or their instruction set might be smaller, but they cannot compute more powerfully. A Turing machine is equivalent to a push-down automaton that has been made more flexible and concise by relaxing the last-in first-out requirement of his stack. At the other extreme, some very simple models turn out to be Turing equivalent, that is to have the same computational power as the Turing machine model. Common equivalent models are the multi-tape Turing machine, multi-track Turing machine, machines with input and output, and the non-deterministic Turing machine as opposed to the deterministic Turing machine for which the action table has at most one entry for each combination of symbol and state. Read-only, right-moving Turing machines are equivalent to NDFAs. For practical and didactical intentions the equivalent register machine can be used as a usual assembly programming language. Choice C machines, Oracle O machines. Early in his paper Turing makes a distinction between an automatic machine its motion, completely determined by the configuration, and a choice machine, whose motion is only partially determined by the configuration. When such a machine reaches one of these ambiguous configurations, it cannot go on until some arbitrary choice has been made by an external operator. This would be the case if we were using machines to deal with axiomatic systems. Turing does not elaborate further except in a footnote in which he describes how to use an A machine to find all the provable formulae of the Hilbert calculus rather than use a choice machine. He supposes that the choices are always between two possibilities 0 and 1. Each proof will then be determined by a sequence of choices I1, I2, in, and hence the number 2n plus I12 n1 plus I22 n2 plus n completely determines the proof. The automatic machine carries out successively proof 1, proof 2, proof 3. This is indeed the technique by which a deterministic Turing machine can be used to mimic the action of a non-deterministic Turing machine. Turing solves the matter in a footnote and appears to dismiss it from further consideration. An Oracle machine or O machine is a Turing O machine that pauses its computation at state O while, to complete its calculation, it awaits the decision of the Oracle an unspecified entity apart from saying that it cannot be a machine. Undecidable PA 166 168. The concept is now actively used by mathematicians. Universal Turing machines. As Turing wrote in Undecidable, PA 128. It is possible to invent a single machine which can be used to compute any computable sequence. If this machine U is supplied with the tape on the beginning of which is written the string of quintuples separated by semicolons of some computing machine M, then you will compute the same sequence as M. This finding is now taken for granted, but at the time it was considered astonishing. The model of computation that Turing called his universal machine U for short is considered by some to have been the fundamental theoretical breakthrough that led to the notion of the stored program computer. Turing's paper contains, in essence, the invention of the modern computer and some of the programming techniques that accompanied it. In terms of computational complexity, a multi-tape universal Turing machine need only be slower by logarithmic factor compared to the machines it simulates. This result was obtained in 1966 by F. C. Henney and R. E. Stearns. Comparison with real machines. It is often said that Turing machines, unlike simpler automata, are as powerful as real machines, and are able to execute any operation that a real program can. What is neglected in this statement is that, because a real machine can only have a finite number of configurations, this real machine is really nothing but a linear-bounded automaton. On the other hand, Turing machines are equivalent to machines that have an unlimited amount of storage space for their computations. As a matter of fact, Turing machines are not intended to model computers, but rather they are intended to model computation itself. Historically, computers, which compute only on their internal storage, were developed only later. There are a number of ways to explain why Turing machines are useful models of real computers. Anything a real computer can compute, a Turing machine can also compute. For example, a Turing machine can simulate any type of subroutine found in programming languages, including recursive procedures and any of the known parameter passing mechanisms. A large enough FSA can also model any real computer, disregarding I/O. Thus, a statement about the limitations of Turing machines will also apply to real computers. The difference lies only with the ability of a Turing machine to manipulate an unbounded amount of data. However, given a finite amount of time, a Turing machine can only manipulate a finite amount of data. Like a Turing machine, a real machine can have its storage space enlarged as needed, by acquiring more disks or other storage media. If the supply of these runs short, the Turing machine may become less useful as a model. But the fact is that neither Turing machines nor real machines need astronomical amounts of storage space in order to perform useful computation. The processing time required is usually much more of a problem. Descriptions of real machine programs using simpler abstract models are often much more complex than descriptions using Turing machines. For example, a Turing machine describing an algorithm may have a few hundred states, while the equivalent deterministic finite automaton on a given real machine has quadrillions. This makes the DFA representation infeasible to analyze. Turing machines describe algorithms independent of how much memory they use. There is a limit to the memory possessed by any current machine, but this limit can rise arbitrarily in time. Turing machines allow us to make statements about algorithms which will hold forever, regardless of advances in conventional computing machine architecture. Turing machines simplify the statement of algorithms. Algorithms running on Turing-equivalent abstract machines are usually more general than their counterparts running on real machines, because they have arbitrary precision data types available and never have to deal with unexpected conditions. One way in which Turing machines are a poor model for programs is that many real programs, such as operating systems and word processors, are written to receive unbounded input over time, and therefore do not halt. Turing machines do not model such ongoing computation well. Limitations of Turing machines, computational complexity theory. A limitation of Turing machines is that they do not model the strengths of a particular arrangement well. For instance, modern stored program computers are actually instances of a more specific form of abstract machine known as the Random Access Stored Program Machine or RASP machine model. Like the universal Turing machine, the RASP stores its program in memory external to its finite state machine's instructions. Unlike the universal Turing machine, the RASP has an infinite number of distinguishable, numbered but unbounded registers memory cells that can contain any integer, Hartmanis, and in particular Cook-Rechau. References at Random Access Machine. The RASP's finite state machine is equipped with the capability for indirect addressing. Thus the RASP's program can address any register in the register sequence. The upshot of this distinction is that there are computational optimizations that can be performed based on the memory indices, which are not possible in a general Turing machine. Thus when Turing machines are used as the basis for bounding running times, a false lower bound can be proven on certain algorithms' running times. An example of this is binary search, an algorithm that can be shown to perform more quickly when using the RASP model of computation rather than the Turing machine model. Concurrency, another limitation of Turing machines is that they do not model concurrency well. For example, there is a bound on the size of integer that can be computed by an always halting non-deterministic Turing machine starting on a blank tape. By contrast, there are always halting concurrent systems with no inputs that can compute an integer of unbounded size. History. They were described in 1936 by Alan Turing. Historical background, computational machinery. Robin Gandy, a student of Alan Turing and his lifelong friend, traces the lineage of the notion of calculating machine back to Babbage and actually proposes Babbage's thesis. That the whole of development and operations of analysis are now capable of being executed by machinery. Gandy's analysis of Babbage's analytical engine describes the following 5 operations: the arithmetic functions plus, a, where A indicates proper subtractions AR equals A0 if YAR permel beta X, any sequence of operations is an operation, iteration of an operation, conditional iteration, conditional transfer. Gandy states that the functions which can be calculated by and are precisely those which are Turing computable. He cites other proposals for universal calculating machines included those of Percy Ludgate, Leonardo Torres y Quevedo, Maurice Dokan, Louis Coufignol, Vannevar Bush, Howard Aiken. However, the emphasis is on programming a fixed iterable sequence of arithmetical operations. The fundamental importance of conditional iteration and conditional transfer for a general theory of calculating machines is not recognized. The Insky-Dunks problem, Hilbert's 10th question of 1900. With regards to Hilbert's problems posed by famous mathematician David Hilbert in 1900, an aspect of problem number 10 had been floating about for almost 30 years before it was framed precisely. Hilbert's original expression for number 10 is as follows. 10. Determination of the solvability of a Diophantine equation. Given a Diophantine equation with any number of unknown quantities and with rational integral coefficients, to devise a process according to which it can be determined in a finite number of operations whether the equation is solvable in rational integers. The Insky-Dunks problem, decision problem for first-order logic, is solved when we know a procedure that allows for any given logical expression to decide by finitely many operations its validity or satisfiability. The Insky-Dunks problem must be considered the main problem of mathematical logic. By 1922, this notion of Insky-Dunks problem had developed a bit, and H. Beeman stated that a most general form of the Insky-Dunks problem is as follows: a quite definite generally applicable prescription is required which will allow one to decide in a finite number of steps the truth or falsity of a given purely logical assertion. Beeman remarks that the general problem is equivalent to the problem of deciding which mathematical propositions are true. If one were able to solve the Insky-Dunks problem, then one would have a procedure for solving many mathematical problems. By the 1928 International Congress of Mathematicians, Hilbert made his questions quite precise. First, was mathematics complete? Second, was mathematics consistent? And thirdly, was mathematics decidable? The first 2 questions were answered in 1930 by Kurt Paragraph-Dell at the very same meeting where Hilbert delivered his retirement speech. The third the Insky-Dunks problem had to wait until the mid-1930s. The problem was that an answer first required a precise definition of definite general applicable prescription, which Princeton professor Alonzo Church would come to call effective calculability, and in 1928 no such definition existed. but over the next 6–7 years Emil Post developed his definition of a worker moving from room to room writing and erasing marks per a list of instructions, as did Church and his two students Stephen Kleene and J.B. Rosser by use of Church's lambda calculus and Gar-paragraph-Dell's recursion theory. Church's paper showed that the Inskey-Dunks problem was indeed undecidable, and beat Turing to the punch by almost a year. In the meantime, Emil Post submitted a brief paper in the fall of 1936, so Turing at least had priority over Post. While Church refereed Turing's paper, Turing had time to study Church's paper and add an appendix where he sketched a proof that Church's lambda calculus and his machines would compute the same functions. But what Church had done was something rather different, and in a certain sense weaker. The Turing construction was more direct, and provided an argument from first principles, closing the gap in Church's demonstration. And Post had only proposed a definition of calculability and criticized Church's definition, but has proved nothing. Alan Turing's A Machine. In the spring of 1935, Turing, as a young master's student at King's College, Cambridge, UK, took on the challenge. He had been stimulated by the lectures of the logician M.H.A. Newman, and learned from them of Gar-paragraph-Dell's work and the Inskey-Dunks problem. Newman used the word mechanical. In his obituary of Turing 1955, Newman writes, "To the question, what is a mechanical process?" Turing returned the characteristic answer, something that can be done by a machine, and he embarked on the highly congenial task of analyzing the general notion of a computing machine. Gandhi states that, "I suppose, but do not know, that Turing, right from the start of his work, had as his goal a proof of the undecidability of the Inskey-Dunks problem. He told me that the main idea of the paper came to him when he was lying in Grantchester Meadows in the summer of 1935. The main idea might have either been his analysis of computation or his realization that there was a universal machine, and so a diagonal argument to prove unsolvability." While Gandhi believed that Newman's statement above is misleading, this opinion is not shared by all. Turing had a lifelong interest in machines. Alan had dreamt of inventing typewriters as a boy. His mother, Mrs. Turing, had a typewriter. And he could well have begun by asking himself what was meant by calling a typewriter mechanical. While at Princeton pursuing his Ph.D., Turing built a Boolean logic multiplier. His Ph.D. thesis, titled Systems of Logic Based on Ordinals, contains the following definition of a computable function. It was stated above that a function is effectively calculable if its values can be found by some purely mechanical process. We may take this statement literally, understanding by a purely mechanical process one which could be carried out by a machine. It is possible to give a mathematical description, in a certain normal form, of the structures of these machines. The development of these ideas leads to the author's definition of a computable function, and to an identification of computability with effective calculability. It is not difficult, though somewhat laborious, to prove that these three definitions, the third is the I-calculus, are equivalent. When Turing returned to the UK, he ultimately became jointly responsible for breaking the German secret codes created by encryption machines called the Enigma. He also became involved in the design of the ACE. Turing's ACE proposal was effectively self-contained, and its roots lay not in the EDVAC, the USA's initiative, but in his own universal machine. Arguments still continue concerning the origin and nature of what has been named by Kleene Turing's thesis. But what Turing did prove with his computational machine model appears in his paper on computable numbers, with an application to the Inskey-Dunks problem. That the Hilbert-Inskey-Dunks problem can have no solution. I propose, therefore, to show that there can be no general process for determining whether a given formula U of the functional calculus K is provable, that is, that there can be no machine which, supplied with any one U of these formulae, will eventually say whether U is provable. Turing's example: if one is to ask for a general procedure to tell us, does this machine ever print 0, the question is undecidable. 1937–1970, The Digital Computer, The Birth of Computer Science. In 1937, while at Princeton working on his Ph.D. thesis, Turing built a digital multiplier from scratch, making his own electromechanical relays. Alan's task was to embody the logical design of a Turing machine in a network of relay-operated switches. While Turing might have been just initially curious and experimenting, quite earnest work in the same direction was going in Germany, and in the United States and George Stibitz. The fruits of their labors were used by the Axis and Allied military in World War II. In the early to mid-1950s, Hao Wang and Marvin Minsky reduced the Turing machine to a simpler form. Simultaneously, European researchers were reducing the newfangled electronic computer to a computer-like theoretical object equivalent to what was now being called a Turing machine. In the late 1950s and early 1960s, the coincidentally parallel developments of Melzack and Lambeck, Minsky, and Shepherdson and Sturgis carried the European work further and reduced the Turing machine to a more friendly, computer-like abstract model called the counter machine. Ilgott and Robinson, Hartmanis, Cook and Recco carried this work even further with the register machine and random access machine model Seguro, but basically all are just multi-tape Turing machines with an arithmetic-like instruction set. 1970 Euro present, the Turing machine is a model of computation. Today, the counter, register and random access machines and their sire the Turing machine continue to be the models of choice for theorists investigating questions in the theory of computation. In particular, computational complexity theory makes use of the Turing machine. Depending on the objects one likes to manipulate in the computations, two models have obtained a dominant position in machine-based complexity theory, the offline multitape Turing machine, which represents the standard model for string-oriented computation, and the random access machine is introduced by Cook and Recco, which models the idealized von Neumann-style computer. Only in the related area of analysis of algorithms this role is taken over by the RAM model. Kantorowicz, 2005, Sweden was the first to show the most simple obvious representation of Turing machines published academically which unifies Turing machines with mathematical analysis and analog computers. See also, notes, the idea came to him in mid-1935 after a question posed by M. H. A. Newman in his lectures, was there a definite method, or as Newman put it, a mechanical process which could be applied to a mathematical statement, and which would come up with the answer as to whether it was provable. Turing submitted his paper on May 31, 1936 to the London Mathematical Society for its proceedings, but it was published in early 1937 and off-prints were available in February 1937. See the definition of innings on Wiktionary, references, primary literature, reprints, and compilations, B. Jack Copeland ed., The Essential Turing, Seminal Writings in Computing, Logic, Philosophy, Artificial Intelligence, and Artificial Life plus The Secrets of Enigma, Clarendon Press, Oxford UK, ISBN 0-19-825079-7. Contains the Turing papers plus a draft letter to Emil Post re his criticism of Turing's convention, and Donald W. Davis corrections to Turing's universal computing machine, Martin Davis, The Undecidable, Raven Press, Hewlett, N.Y. Emil Post, Finite Combinatory Processes a Euro Formulation 1, Journal of Symbolic Logic, 1, 103 a Euro 105, 1936. Reprinted in The Undecidable ppA 289 ff. Emil Post, Recursive Unsolvability of a Problem of Few, Journal of Symbolic Logic, Volume 12, ppA 1 a Euro 11. Reprinted in The Undecidable ppA 293 ff. In the appendix of this paper Post comments on and gives corrections to Turing's paper of 1936 a Euro 1937. In particular see the footnotes 11 with corrections to the universal computing machine coding and footnote 14 with comments on Turing's first and second proofs. Turing, A.M. on computable numbers, with an application to the Entscheidungs problem. Proceedings of the London Mathematical Society 242, 230 a Euro 265 doi, 10.1112s2-42.1.230a. On computable numbers, with an application to the Entscheidungs problem, a correction. Proceedings of the London Mathematical Society 243, 544 Euro 6 doi, 10.1112S2-43.6.544a. Reprinted in many collections, for example in the undecidable PPA 115 Euro 154. Available on the web in many places, for example at SCRIBD. Alan Turing, 1948, Intelligent Machinery. Reprinted in Cybernetics, Key Papers. Ed. C. R. Evans and A. D. J. Robertson. Baltimore, University Park Press, 1968. PA 31. F. C. Henny and R. E. Stearns. Two-tape simulation of multitape Turing machines. JACM, 13, 4, 533 Euro 546, 1966. Computability Theory, Boulos, George. Richard Jeffrey. Computability and Logic. Cambridge UK, Cambridge University Press. ISBN A0-521-20402 Exeter, Boulos, George. John Burgess, Richard Jeffrey. Computability and Logic. Cambridge UK, Cambridge University Press. ISBN A0-521-00758-5. Some parts have been significantly rewritten by Burgess. Presentation of Turing machines in context of Lambek abacus machines, and recursive functions, showing their equivalence. Taylor L. Booth, Sequential Machines and Automata Theory, John Wiley & Sons, Incorporated, New York. Graduate-level engineering text. Ranges over a wide variety of topics. Chapter 9 Turing machines includes some recursion theory. Martin Davis. Computability and Unsolvability. McGraw-Hill Book Company, Incorporated, New York A. On pages 12 a Euro 20 he gives examples of 5 tuple tables for addition, the successor function, subtraction, proper subtraction, the identity function and various identity functions, and multiplication. Davis, Martin. Ron Siegel. Elaine J. Wiewicker. Computability, Complexity, and Languages and Logic, Fundamentals of Theoretical Computer Science. San Diego, Academic Press, Harcourt, Brace & Company. ISBN A0-12-206382-1. Henny, Frederick. Introduction to Computability. Edison Euro Wesley, Reading, Mass. QA 248.5 H4 1977a. On pages 90 a Euro 103 Henny discusses the UTM with examples and flow charts, but no actual code. John Hopcroft and Jeffrey Ullman. Introduction to Automata Theory, Languages, and Computation. Edison Euro Wesley, Reading, Mass. ISBN A0-201-02988X. A difficult book. Centered around the issues of machine interpretation of languages, NP completeness, etc. Hopcroft, John E. Rayab Matwani. Jeffrey D. Ullman. Introduction to Automata Theory, Languages, and Computation. Reading, Mass. Edison Euro Wesley. ISBN A0-201-44124-1. A distinctly different and less intimidating than the first edition. Stephen Kleen, Introduction to Metamathematics, Northern Euro Holland Publishing Company, Amsterdam, Netherlands, 10th impression. Graduate-level text. Most of Chapter 13 Computable Functions is on Turing machine proofs of computability of recursive functions, etc. Knuth, Donald E. Volume 1/Fundamental Algorithms, The Art of Computer Programming. Reading, Massachusetts Edison Euro Wesley Publishing Company A. With reference to the role of Turing machines in the development of computation, see 1.4.5 History and Bibliography PPA 225 FF and 2.6 History and Bibliography A 456 FF. Zohar Manor, 1974, Mathematical Theory of Computation. Reprinted, Dover, 2003. ISBN 978-0-486-43238-0. Marvin Minsky, Computation, Finite and Infinite Machines, Prentischer Euro Hall, Incorporated, New Jersey, 1967. See Chapter 8, Section 8.2 Unsolvability of the halting problem. Excellent, that is relatively readable, sometimes funny. Christos Papademetria. Computational Complexity. Addison Wesley. ISBN A0-201-53082-1. A Chapter 2, Turing Machines, pp. 19 €56. Michael Sipser. Introduction to the Theory of Computation. PWS Publishing. ISBN A0-534-94728-X. A Chapter 3, The Churchie Turing Thesis, pp. 125 149. Stone, Harold S. Introduction to Computer Organization and Data Structures. New York, McGraw-Hill Book Company. ISBN A0-07-061726-0. Peter van Emtboers 1990, Machine Models and Simulations, pp. 3 €66, in January van Leeuwen, ed., Handbook of Theoretical Computer Science, Volume A, Algorithms and Complexity, the MIT Press Elsevier, Place. ISBN 0-444-88071-2. QA76H279 1990. Valuable survey, with 141 references. Church's Thesis, Nachum Dershowitz. Yuri Gurevich. A Natural Axiomatization of Computability and Proof of Church's Thesis. Bulletin of Symbolic Logic 14. Retrieved October 15, 2008. Roger Penrose. The Emperor's New Mind. Oxford University Press, New York. ISBN A0-19-851973-7. Small Turing Machines, Rogozin, Yuria, 1998, A Universal Turing Machine with 22 States and 2 Symbols, Romanian Journal of Information Science and Technology, 1, 3, 259 €265, 1998. Stephen Wolfram, 2002, A New Kind of Science. Wolfram Media, ISBN 1-57955-008-8, Broomfield, Jeff, Student Snags Maths Prize, Nature, October 24, 2007. Jim Giles, Simplest Universal Computer wins student $25,000, New Scientist, October 24, 2007. Alex Smith, Universality of Wolfram a unregistered trademark S2. 3 Turing Machine, submission for the Wolfram 2, 3 Turing Machine Research Prize. Vaughan Pratt, 2007, Simple Turing Machines, Universality, Encodings, etc., FOM email list. October 29, 2007. Martin Davis, 2007, Smallest Universal Machine, and Definition of Universal Turing Machine FOM email list. October 26, 27, 2007. Alistair Urquhart, 2007 Smallest Universal Machine, FOM email list. October 26, 2007. Hector Zenel, 2007 Smallest Universal Machine, FOM email list. October 29, 2007. Todd Rowland, 2007, Confusion on FOM, Wolfram Science Message Board, October 30, 2007. Olivier and Mark Raynaud, 2014, A Programmable Ultra-Mechanical Turing Machine with a Large Number of Diagrams Limos Laboratory of Blaise Pascal University. Other, Martin Davis. Engines of Logic, Mathematicians and the Origin of the Computer W. W. Norton and Company, New York. ISBN A0-393-32229-7. Robin Gandy, The Confluence of Ideas in 1936, ppA 51 €102. And Rolf Herken, see below. Stephen Hawking, 2005, God Created the Integers, The Mathematical Breakthroughs That Changed History, Running Press, Philadelphia, ISBN 978-0-7624-1922-7. Includes Turing's 1936–1937 paper, with brief commentary and biography of Turing as written by Hawking. Rolf Herken. The Universal Turing Machine a half-century survey. Springer Verlag. ISBN A3-211-82637-8. Andrew Hodges, Alan Turing, The Enigma, Simon & Schuster, New York. Cf. Chapter The Spirit of Truth for a History Leading to, and a Discussion of, His Proof. Ivars Peterson. The Mathematical Tourist, Snapshots of Modern Mathematics. W. H. Freeman and Company, New York. ISBN A0-7167-2064-7. Paul Strathen. Turing and the Computer The Big Idea. Anchor Books Doubleday. ISBN A0-385-49243. Hao Wang, A Variant to Turing's Theory of Computing Machines, Journal of the Association for Computing Machinery 4, 63 €92. Charles Ptzold, Charles, The Annotated Turing, John Wiley & Sons, Incorporated, ISBN 0-470-22905-5. Aurora, Suniev. Barak, Boaz, Complexity Theory, A Modern Approach, Cambridge University Press, 2009, ISBN 978-0-521-42426-4. Section 1.4, Machines as Strings and the Universal Turing Machine, and 1.7, Proof of Theorem. 1.9, Kantorowicz, Isaiah Pinchers. A Note on Turing Machine Computability of Rule-Driven Systems. Sigect News 36, 109 €110 doi, 10.1145/1,107,523.1107525. External links, Haswinkel, Mikhail, ed., Turing Machine, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. Turing Machine on Stanford Encyclopedia of Philosophy, detailed info on the Churchie Turing hypothesis, Web Turing Machine web application to construct and execute Turing machines, Turing machine-like models in molecular biology, to understand life mechanisms with the DNA tape processor. The Turing Machine Summary about the Turing machine, its functionality and historical facts, the Wolfram II, 3 Turing Machine Research Prize Stephen Wolfram's $25,000 prize for the proof or disproof of the universality of the potentially smallest universal Turing machine. The contest has ended, with the proof affirming the machine's universality. Turing Machine Causal Networks by Enrique Zini, Wolfram Demonstrations Project. Turing Machines at DMOZ, Purely Mechanical Turing Machine.